This is lecture 9G on the equations, differential equations for draining liquids out of tanks for Calculus 2. Now the differential equation governing the draining of fluid from a tank, and we're just going to say under gravity, not through some kind of suction or anything, but just going to be draining the fluid out from as though you have a big tank and there's a hole or an outlet pipe at the bottom of it, and you just let the fluid drain out. That's the problem we're going to solve here. And what we end up with for a differential equation is the rate of change of the volume. This will give us the rate at which the fluid is draining from the tank, and it depends on two things. It depends on the fluid level inside of the tank, and it depends on Torricelli's law. So first I'm going to derive Torricelli's law for you. Okay, the reason I'm going to derive it is that sometimes it's presented for special circumstances, and if you see how it's derived here, you'll be able to adapt it to any kind of situation. Okay, so what we're going to start with is the height of the fluid in the tank, and we're going to write the potential energy for the height of the fluid in the tank as mass times the acceleration due to gravity times the height of the fluid in the tank times h. Okay, this is potential energy here, and g is the acceleration due to gravity on any planet or moon or wherever you need it to be. Okay, this is wherever you're draining this fluid. Okay, now we're going to let the v be the velocity of the fluid draining from the tank. There's kinetic energy associated with that, and the kinetic energy is 1/2 mv squared. Now equate these two. Let me get the pen so I can do that. So here I would have 1/2 mv squared is equal to mass times acceleration due to gravity times h. The m's obviously cancel, and we end up with v equals, or rather v squared is 2gh, taking the square root. There we go. So now we have an expression for the velocity of the fluid as it exits the tank. Torricelli's law, though, is not about the velocity of the fluid as it exits the tank. Instead, it's about the flow. Flow being the rate of change of volume. This is what we're looking for. Okay, so if you knew, alright, I've got an outlet pipe, see, or a hole cut in the bottom of this tank, and I know the fluid's coming out with some velocity. We're not going to say it's laminar flow, we're just going to let it flow out at some velocity that we calculated on the previous page, and I want the volume that's coming out. If I take that velocity and then multiply it by the cross-sectional area of the outlet pipe or the hole, then I will get, that will give me the rate of change of the volume. In case you don't see that right off, let's look at it dimensionally. Okay, velocity has units of meters per second. The area is meters squared. So if I multiply those two together, I end up with units of cubic meters per second. Right? That is a rate of change of volume. Volume is cubic meters. Right? So I'm going to multiply this expression that I had before, kind of broken it out a little bit differently. Remember that the velocity was the square root of 2 times acceleration due to gravity times h. Right. I multiply that by the cross-sectional area of the outlet. Say you have a circular outlet pipe of radius r, its area then is pi r squared. So here's Torricelli's law for a circular outlet pipe. You may not have such a thing, but say you do, then you would, the area gets replaced by pi r squared, then you have the square root of 2g from your velocity expression, and then I broke out the square root of h because that's what's going to be part of our differential equation. So I just broke that out by itself. Now say you want to, this is per second, and say you want it to be per minute, then just multiply by 60. That's it. Okay, so r is the radius of this outlet pipe right here. That's r. Okay. Pi r squared gives you its area. Square root of 2g came from the expression for velocity, and I have a square root of h which I've isolated outside. There we go. That's Torricelli's law for a circular outlet pipe with dimensions then unit time being in minutes.